Dear student, I welcome you in the class of System Programming. In today's lecture, we are going to start with unit number 6 and the topic is the code optimizer. This is the content of unit number 6. Unit number 6 is focused on code generation and the code optimization. We are going to refer a Ullmann-Setti book, Compiler Principle, Techniques and Tools. Chapter number 8 is focused on your code generation technique and few content of chapter 8 and the chapter 9 is used for the code optimization. So in the today's lecture we are going to look out for the first code optimization and the two different ways of your code optimization like machine independent techniques and machine dependent techniques. So what is a code optimizer? As we have seen that the compiler converts the high level language program into the target program, that is machine code. So we have seen that your compiler goes on different phases and we have seen that the lexical analyzer, syntax analyzer, semantic analyzer and intermediate code generator is called as the front end and the back end is your code optimizer and code generator. So in the code optimization is nothing but the prior phase of your code generator. It can be happen that your code optimization and code generation will have multiple passes over intermediate code whichever generated by intermediate code generator to generate target programs. So what is code optimizer? We are expecting that whatever the output of code generator is your intermediate representation. So that intermediate representation code directly can be converted into the target code, that is machine code. But it can be happen that whatever the temporaries we people are creating in the 3 address code, then they can be unnecessarily. So we have to think that can we optimize the code in such a way that your target code consumes less CPU or memory. Also we are looking for that can we increase the performance of your program, means we can execute, we will get the output as faster. So the basic things of the code optimizing the code is that we are transforming the program into that intermediate representation to the modified intermediate representation. But we need to take care that there should not be any change in the meaning of your program. The optimization should increase the speed of your program and optimization itself be fast and it should not delay the overall compiling process. At the beginning, user can change or rearrange the code for the better code or faster code we are expecting. But it can be happen after intermediate code, compiler can modify the intermediate code by address calculation and by improving the loops. While producing the target machine code, compiler can also use the memory hierarchy and CPU register. Then it is called as machine dependent code optimizer. And if we are not using memory or the CPU, then it is called as machine independent code optimization. The result of optimization is that we can transform the program in such a way that we will increase the performance or efficiency of your target program. And definitely we are requiring the list size. And definitely the computation memory speed also going to be reduced. As we have now seen that the code optimization techniques are of two ways, machine independent technique and machine dependent technique. In the machine independent technique, which does not involve any CPU register or any absolute locations. But in machine independent techniques, we are not using any CPU registers, but machine dependent techniques, we are involving some CPU registers and some absolute memory references. Let's see in detail machine independent technique. Let's look at this example that in machine independent techniques we are not involving any CPU register. Look out this do while statement. So if you observed, this do is equal to item is equal to 10 and the value is equal to value plus item. These two statements will be repeatedly executed until the value will not become 100. If we are assuming that the value is assigned to 0, means these two statements are going to be executed 100 times. Means if you are going to count the frequency of item is equal to 10, it is going to be executed 100 times and the value is equal to value plus item is also 100 times. But if you observe that item 10 is always the constant, it does not impact on this while looping statement. So is it possible that we can keep outside this do while statement? Of course it is. And we are optimizing the code in such a way that instead of this item 10 is going to be executed 100 times, it is going to be executed only once. and the value is equal to value plus item is will be 100. Means if you observe this code, it requires the frequency count is 200, but in this case the frequency count is 101. Means we have optimized the code. So these are the different examples of your code optimization, like a common sub-expression elimination, dead code elimination, structure simplification, constant folding, strength reduction, loop optimization, and code inline, etc. Let me see one by one. Common sub-expression elimination. Here we are looking for that is there occurrence any expressions in that particular block. Means we are going to check out is it the same expression is being computed. If it is being computed inside a one block, then it is called as local common sub-expression. And if it is executed on the globally, means in the throughout your whole structure, then it is called as a global common sub-expression. These points we are going to look out in detail in the point, basic block and flow graph. In the local common sub-expression, that here we are going to compute that T1 A of I plus 1 is equal to B of I plus 1. Means the value of I plus 1, whatever the indices we are getting, that value will be assigned to A of I plus 1. So for this reason, we are writing the three address code like this. T1 is equal to I plus 1. T2 is equal to B of T1, T3 is equal to I plus 1, and A of T3 is equal to T2. But if you have observed the T1 and T3 are having the same sub-expression like I plus 1, then it can be possible that T3 can be replaced by the T1 like this, and we are not rewriting this T3 anywhere. So our resultant expression becomes T1 is equal to I plus 1, T2 is equal to B of T1, and A of T1 is equal to T2. Look out the same thing. Here A is equal to B plus C, A is equal to C plus D plus B. Means we are computing B plus C here also and B plus C here also. But if we will apply a general 3 address code, then we are getting these statements like a 3 address code. A is equal to B plus C, T is equal to C plus D, and the value of T will be added with the B. Then we can reduce or rewrite the code like this: A is equal to B plus C and E is equal to A plus D. So one more example. Now this is the time for the reflection quiz. I expect the student that you pause the video and kindly solve this example. I hope you have paused the video and you have identified that which are your common sub expression and what is your resultant optimized code. Is it? Yes, of course. So T1 is equal to 4 multiplied by I and T4 is equal to 4 multiplied by I is being computed repeatedly. Means instead of T4 we can use T1, and this becomes the final optimized code. And here the common sub expression 4 multiplied by I is being removed. Constant folding. We can evaluate the constant expression at the compile time itself. Sometimes in our coding we are writing that C is equal to 1 plus 3. That means 1 plus 3, the result is 4, can be done at the compile time itself. Copy propagation. The value of B is equal to 3, then C is equal to 1 plus B and D is equal to 1 plus 3. Sorry, constant propagation. So here we are writing the value of B is the constant. So can we write C is equal to 1 plus 3 as it is instead of B, and D is equal to 3 plus 3 as it is? Of course we can do. Means value of B is the constant, then we can replace the value of B as it is during the compile time. Look out here. If you are writing I is equal to 4, then your the constant folding is T1 is equal to I plus 4. So result of T1 is nothing but that T1 is equal to 5, and we can use this T1 is equal to 5 as a modified intermediate code. But if you have observed, again we can apply the T2 is equal to B of T1. As the value of T1 is a constant, we are going to replace this T1 by 5 and we are getting this resultant expression. So here we not need T1 is equal to 5. That's why this becomes our final optimized code. Copy propagation. If you are writing the statement x is equal to y, that means the value of y is copied to x and then we are using the value of x. So is it possible that we can use the value of y directly? Like this. If we are having x is equal to y or c is equal to 1 plus x, d is equal to x plus c, and again we are writing x is equal to y. Is it possible that we can remove or we can rewrite the statement instead of copying y is equal to x, directly write down the value of x will be replaced by the y. So here we are identified that we are removing that your copy propagation. Also we can use the algebraic identification. If you have observed, we are writing that x plus 0. The meaning of x plus 0 that the value of x itself, or we are writing 0 plus x. So here we are applying some arithmetic identities so we can eliminate the computation. So this is nothing but that we are removing such expressions and expression, and that value will be written as it is. Like this, x multiplied by 1 or 1 multiplied by x will be replaced by x as it is. X division by 1 means that number itself, or x subtraction 0, that number itself. Similarly, we can use the strength reduction. In the arithmetic expression, if you have observed, then there are some expressions are requiring the more time. That operators we are calling as an expensive operator. If you look out or compare that your multiplication and plus, then you are getting that the plus is the cheaper expression and multiplication requires more computation. If you look out for your raised to operator and multiplication, so raised to is the expensive and multiplication is the cheaper. So is it possible that can we replace a more expensive operator by the cheaper one? If you look out the example x raised to 2, means can we write or replace this x raised to 2 by x multiplied by x. 2 multiplied by x is nothing but that x plus x. If I am going to say 2 multiplied by 4, the result is 8. 2 multiplied by 3, the result is 6. So can we write directly 3 plus 3 or 4 plus 4? That means 2 multiplied by x can be rewritten as x plus x. Similarly, for the division operator is more expensive. That's why we are using multiplied by 0.5 will work as a division. So here in this for loop, observed here, you are getting that these are some initializations or statements of your for loop. Then now we have to compute this count statement. So here this count statement is consist of I multiplied by 7. So multiplication operator requires more time. So can we write that 7 is going to be stored in some temporaries. That's why we are rewriting the temp is equal to 7 outside your for loop. And count is equal to temp. The value of temp will be assigned to count, and every time the temp value will be assigned by 7. Also use of algebraic identities. If you are having that like a constant propagation 2 multiplied by 3.14, we can replace it by the value as it is. Means we have to evaluate that constant of folding into that expression at the compile time itself, and we have to replace that constant expression by their value. Next interesting part is a dead code elimination. Before, generally we are writing that code, and many times we are writing the code in such a way that that code will never get executes. So that is nothing but called as the dead code. Dead code is one or more than one code which are either never be executed or never unreachable. And if they are executed, their output is never being used. That's why the dead code plays no role in our program, and that's why we can easily eliminate them. Look out here. If we are writing b is equal to 3, c is equal to 1 plus 3, and d is equal to 3 plus c. Have we used the value of b here? And if we are not using anywhere the value of b, then why we are using b is equal to 3, and that b is equal to 3 can be removed by using dead code elimination technique. Similarly, if we are writing the code which never used, we are writing if I is false, if a value is false, then the value of a is 5. But if the value false will never get, then a is equal to 5 will not be executed. Then why do we convert a of 5 into the target code? Better thing, let me remove it. So this is the Peephole optimization. It is a simple but effective technique for the locally improving the target code. It is a method for trying to improve the performance of your target code. So here we are going to look out the characteristics of the Peephole optimization. It is having redundant instruction elimination, that is common subexpression elimination, flow of control, algebraic simplification, and use of machine idioms. If you will look out that the shorter sequence of the target instruction and replacing this instruction by the shorter or the faster sequences is the code Peephole optimization. We have already covered this topic, that the constant folding x is equal to 32 and x is equal to x plus 32. Let me rewrite that x is equal to 64 as it is. If you are writing the general other statement, we are writing the statement is go to L2, and while we are going for the L2, we are writing L2 is equal to x plus 1. Then is it possible that we can rewrite directly that the go to L1 instead of writing that L1 is equal to go to? Peephole optimization, algebraic simplification, dead code elimination, and strength reduction. So I hope my students have understand that what are the different machine independent code optimization technique. So dear student, kindly solve some examples on it. Thank you. Have a nice day. Happy learning.